everybody, and welcome to today's webinar presentation, App Hardening, Preventing Hackers from Accessing Your Code, brought to you by Guardsquare. I would like to introduce you to our presenter, Jonas Hebels. Jonas helps educate and build awareness on the mobile application security landscape. In addition to his knowledge sharing, he assists developers integrating and configuring Guardsquare mobile app security solutions in their projects. Jonas has a master's in engineering technology.
Thank you. So in today's webinar, we'll cover an overview on the mobile threat landscape, and we'll also take a look at two examples, one for a static attack and one for a dynamic attack. After that, we'll take a look at some case studies and real-life examples on where stuff did go wrong for developers of mobile applications. That will be followed with an overview on some do-it-yourself implementation solutions on how you can prevent rooted devices or debuggers from attacking your application. But we'll also cover why it would probably be a bad idea to go ahead with that. At the end, we'll cover an overview on our three products, DexGuard, IXGuard, and ThreatCast. So the current mobile threat landscape consists out of these two main categories. There are the static analysis attacks, in where attackers are going to decompile the application on their own computer, and they're going to take a look at your source code. They might try to spot any vulnerabilities there or try to spot anything they could possibly change in such a way that the app behaves in a more desirable way. For example, they can try to patch out a license check, tamper with the payment system, and so on. On a dynamic analysis attack, the attacker is going to run the application on a test device, which gives the advantage of attaching debuggers and also to hook certain methods of your application. Hooking, as you probably already know, is another technique to change the implementation of that particular part of the application. Lastly, the network attacks, they can also be seen as dynamic analysis attacks, since we also need a test device for that. There, the attacker is going to perform a so-called man-in-the-middle attack to take a look at the traffic between your application and your backend service. This might give some useful information, and it might be of use to perform later a larger attack to your backend server. These types of attacks can come from anywhere. There might be malware installed on the device that's trying to interact with your application. Also, keyloggers and spyware may be present on the device trying to sniff users' credentials, but also other security-sensitive information that the user is entering in your application. And then there is also the malicious user to protect your app from. Malicious users can try to reverse engineer your application and change its behavior in a more desired way. The parts that are often being targeted is, of course, your intellectual property of your application. Any stored keys inside the application, think about cryptographic keys, API keys, and so on. Also, the authentication mechanism might be a target. It could be really useful if you could somehow bypass that, of course. There is the communication between the app itself and the backend that might hold some security-sensitive information that is of use to attackers and malicious users. And of course, if applicable, it would also be nice for an attacker to tamper with the advertisements in such a way that the revenue of these advertisements gets transferred to his account instead of yours. Static analysis can be done with a lot of tools. There are open source tools available out there, but also commercial tools. Some examples are IDA Pro, Hopper, APK Tool, DexDump, DexDujar, etc. Here we see an example of where we used Android Studio to disassemble a sample application, an open source application. As you can see, Android Studio can be used to easily navigate through the different packages, classes, and methods that are available inside this application. It's very useful to gain some insights in this application and to, well, get an understanding on what we want to change in order to benefit us as a malicious user. Dynamic analysis, on the other hand, requires a test device. That gives the advantage that the malicious user can attach a debugger to the app to read out the memory. There might be some decrypted values of certain strings stored in there. Or he can also hook the application with tools like Frida, Exposed, Fishhook, and so on to make a license check, for example, always return true. There are also network analysis tools like Wireshark and Burp Suite available that will allow you to intercept the traffic between the application and the backend server and take a look on what kind of information is being transferred to the server or back to the app. Here we see an example on dynamic analysis. This is a Frida script that you can see here for an iOS application. Here we hooked the instance method is premium of the interface user, and we changed its behavior in such a way that this will always return true. This will result, if we hook the application and run this script, that particular application will think that we are premium users, even though we never paid for that particular application. Let's take a look at some case studies on how that would practically go. For example, API key extraction or cryptographic key extraction. First of all, the attacker would need to download the application from the iOS App Store or the Google Play Store. In case we're talking about iOS, it would be necessary to obtain a decrypted version of the application, which can be easily done using, for example, Clutch on a jailbroken device. Once that's done, the attacker can start analyzing the application, and he might try to search for occurrences like API, secret, token, and so on that might reveal an API key that is belonging to your company. Of course, some services that will charge your company depending on the amount of requests that were incoming from your API key. If the attacker would use that API key in its own applications or sell it to other people, then of course your company gets charged for that use of the service, and that would be a loss for your company. The attacker might also be interested in inserting malicious code in the application. So after downloading and decrypting the application, he might, for example, insert code that performs a DDoS attack on certain targets. Unknowing users might be tricked into downloading the actual cloned version of the application, and they might become part of the DDoS attack without them knowing. Another example is the theft of users' credentials. So here again, it would be necessary to obtain a copy of your application and change it in such a way that instead of logging in a legitimate user, the credentials get passed to a server of the attacker. The attacker will distribute that changed application, and if the user is tricked into believing that this is the real application, he will lose his credentials. Let's say, for example, that you offer a paid video streaming service, then the attacker can use that service for free, or even worse, he can pass these credentials on to other users, maybe even for free on the internet, that can then make use of your service for free. Now you might be wondering if this actually happens in real life, and the answer is yes. We'll take a look at some examples where it went wrong in real life, and of course this is all public information, so if you would Google the names of these applications, you'll come across the same articles as we read and made this presentation with. So for example, there are the apps on iOS, PhotoVault and Keepsafe. They kind of behave in a similar way. They allow a user to store some photos in a secure vault, which is protected with a PIN number that you need to enter before the app can be opened. Unfortunately, there are a couple of vulnerabilities in this application. First of all, the password is stored in an insecure way, and by using a jailbroken device, you can actually navigate through the directories of that application and just read out that file that contains the password in plain text. Another possibility is using a tool like Script or Frida to call the dismiss lock screen method from there, and in that case the lock screen will disappear even though you never entered the code correctly. So what went wrong here? Obviously there was no strong protection against static analysis, leaving these methods that dismiss the lock screen revealed. It's therefore an easy target. There was also no protection against hooking and or swizzling, allowing tools like Script or Frida to interact with this application. And lastly, no insecure storage of the password was implemented either. So in general, you could summarize that no multi-layered approach was taken here. Another example on Android is a Pokémon GO app. This app is probably a bit better known across a wide audience. So Pokémon GO is a game for which you need to walk through the city and catch different Pokémons, of course. There are a couple of cheaters in the game, though, that use an overlay with a joystick that will allow to spoof their location in such a way that they can actually play the game from their couch. Pokémon GO thought that this was, of course, unfair advantage, and they tried to block that kind of behavior. Spoofing GPS locations is especially easy on rooted devices, so they implemented a root check themselves, and if the check detected that the app was running on a rooted device, the app would close. Unfortunately, that was a really basic implementation, and they didn't think about implementing any root hiding techniques, detection mechanisms. So if the user would use root cloak or McGisk hide, they could actually just keep on using Pokémon GO. Of course, since these tools use hooking on the background, they also didn't implement protection against hooking. And in general, we can again say that no multi-layered approach was taken here. Another example on Android is the 7Pay app. The 7Pay app is, if I recall correctly, mostly used in Asia to perform payments with. There was unauthorized access to users' accounts and money got actually stolen. At the moment, it's still not really clear what exactly happened, but some possible scenarios are clones that were distributed, sniffing users' credentials, maybe a simple man-in-the-middle attack on a public network, for example, or even an overlay attack that sniffed the password that the user was entering on his device. So in those cases, 7Pay wouldn't have implemented, for example, tampering detection. The communication between the app and the backend wasn't hardened with SSL pinning. And of course, there was also no protection against overlays or keyloggers. So in general, we can again say there was no multi-layered protection for this application. A last example, also a well-known application, WhatsApp. On both Android and iOS, commercial spyware was inserted in this application. That granted access to these malicious users to the microphone, camera, messages, email, location, and other data of the users of WhatsApp. Of course, this is reputational damage for WhatsApp, and this might even lead in people abandoning your application. So what went wrong here? Obviously, WhatsApp didn't implement any tampering detection. Also, no code integrity protection preventing hooking, swizzling, and so on was implemented, making them vulnerable for such attacks. In general, we can again summarize this, that no multi-layered approach was taken here. So let's take a look at some do-it-yourself implementations to detect both rooted devices as well as debuggers on both Android and iOS, and why it's not a good idea to implement this yourself. Here on the left-hand side, you can see a very basic check that will allow you to detect if a device is jailbroken. The check will try to open a shell with root access, and if that succeeds, it's of course a very clear sign that this device is jailbroken. On the other hand, this does not mean if this check fails that the device is not jailbroken. And the reason for that is because this is a really easy recognizable check. It always looks the same. It is not inlined, and it's very easy to hook as it's commonly known. For example, you can hook the method system here or the function system here, and you can make sure that this always returns 0, even though it actually would return 1, and then you have bypassed this particular jailbreak detection technique. On Android, we can use a similar approach by searching for files like zoo, busybox, superuser.apk, kingouser.apk, and so on. Again, if we find such a file, this is a clear indication that the device is rooted. On the other hand, it does not mean that if we do not find these files that the device is not rooted. The reason for that is because, again, this is a really basic check. It's easy recognizable. It always looks the same. You can hook this by hooking the file exist implementation and changing it in such a way that if somebody searches for these well-known root binaries, let's call them, that you always return a value indicating that these binaries do not exist. This is actually something that's part of rootcloak, so it's easy to use. You can simply install rootcloak on your device and hide your root that way. In a very similar way, there are also snippets available on the internet that will allow you to deny ptrace, a debugger to attach to your iOS application. That snippet is the one you can see here on the left-hand side, but again, it's a very basic implementation that looks always the same. It is not inlined, and you can easily bypass this by hooking first the DLSym method here. And if the symbol ptrace is passed, you can actually return a fake ptrace to that method. That ptrace will be denied to attach to your application, and you can further debug it with the real debugger. On Android, such detection techniques does also exist. You can simply call debug.isDebuggerConnected to detect if a debugger is attached to your Android application. Again, if this returns true, it's a clear indication that the debugger is there, but on the other hand, if this returns false, that does not mean that no debugger is connected at all. Again, it's very easy to recognize also for malicious users, and it's very easy to hook the isDebugger connected method and make sure that this always return false. Let's take a brief overview on the solutions that we offer here at Guardsquare that will protect your application against this kind of static and dynamic analysis. The first tool we have available is DexGuard. This tool will harden your Android application, and it provides you a raft feature set that will protect your app from dynamic attacks. It will also provide you obfuscation and encryption techniques that you can apply to the security sensitive parts of your application to protect it from static analysis. We offer an SSL pinning solution to implement network hardening. And on top of that, we also shrink and optimize the app to make it smaller and faster. You can use DexGuard on regular Android apps, but also on parts developed with the Android NDK in, for example, C++. We're also compatible with hybrid setups, such as Cordova, Ionic, and React Native, and here we can protect the JavaScript code as well. We're also compatible with Unity applications. DexGuard's static protection features integrate in the build process as a Gradle plugin, but we are also compatible with Ant and Maven. And the rest features set can be implemented for apps either by using a runtime library, making some very simple API calls to verify if the device is rooted, if the app is hooked, and so on. Or you can use the automated injection approach, and in that case, no code changes are needed at all. The checks will be inserted randomly through the code during the build time, and by default, they will make the application crash if they detect such a threat. But you can also change the behavior there by implementing a callback to a Kotlin or Java function. For SDKs at the moment, only the runtime library approach is possible for the RASP feature set. We support the languages Java, Kotlin, C++, as well as JavaScript in hybrid applications. Now you might be wondering on how much DexGuard is going to have an impact on the performance of your application, and also there we have great news for you. DexGuard tends to shrink the size by 5 to 70% and increase the speed by 10 to 20% thanks to the shrinking and optimization steps. It's backwards compatible with ProGuard, so if you have already developed any keep rules for ProGuard, you can simply reuse those in DexGuard. The integration effort for completely new users takes about 2 to 3 weeks to get a fully hardened result, but of course, if you're already used to ProGuard, it will probably be less. We also have a tool to harden iOS applications. That would be DexGuard. DexGuard provides you a raft feature set to protect your app from dynamic threats such as hooking, jailbroken devices, debuggers, and so on. And will also protect the app from static analysis with the obfuscation features. So we can, of course, protect regular iOS apps, but also hybrid setups such as with Cordova, React Native, and Ionic. That we can protect the JavaScript too, and we also offer protection for Unity applications. In contrast to DexGuard doesn't really integrate in the build process. It comes as a post-build command line tool. It will take your SDK or application as an input together with the configuration, and it will produce a protected IPA framework or dialib as an output. The languages we currently support are Swift, Objective-C, and JavaScript, and there are two platform considerations that you need to take into account. We need you to use a recent version of Xcode, Xcode 10.x or later, and bitcode is required for your own source code and preferably as much libraries as possible. The performance overhead is none if you apply the protection to only the security sensitive parts of the application. And again, just as with DexGuard, the integration effort is about 2 to 3 weeks for new users. ThreatCast is our monitoring system that can report back on dynamic threats that occurred to your application in real time. It's available for both Android and iOS, but it's important to mention here that you need to use DexGuard and or DexGuard to be able to use ThreatCast. Once a dynamic threat is detected, for example, somebody tried to hook your app or tampered with your app, that will be reported to ThreatCast, and you can analyze that data in an online cloud environment. We report on breaches against environment integrity, app integrity, and code integrity, and you can monitor the data on different views like a timeline. You can show it on a world map to see what countries are the most threats coming from, and so on. The platform consideration, or there are no platform considerations actually, and the integration effort is very easy. Simply copy pasting the API key of ThreatCast to the configuration files of DexGuard and DexGuard is sufficient. From there on, the tools will know what to do with them, and they will integrate the proper API calls for you. That's it for our webinar today. I would like to open some time for a Q&A.
Perfect. Thank you, Jonas, for that wonderful presentation. First question from our audience today is, how do your tools differ from the DIY implementations?
So our tools, well, they will first obfuscate the different checks. Also, for example, on iOS, we offer a combination of 400 checks that will be selected randomly at build time, and they will be inserted multiple times randomly through the app as well as in the entry points. So they will be more frequently added to the applications. They will not always look the same, and they are inlined. On top of that, we also use a multi-layered approach. So simply hooking these kind of checks out is not going to work, because that would trigger yet another feature, code integrity. And so in that way, the features also protect each other.
Awesome. Thank you for that response. Our second question today is, do your tools require an internet connection?
No, with the exception of ThreatCast. So DexGuard and DexGuard can completely run offline on your local machine. ThreatCast, of course, does require an internet connection for your end users. There will be a call to our backend server once a threat is detected. And if you choose so, also once a day for every active users, so that you can compare the daily active users with the amount of threats that are incoming to your application.
Perfect. That's great to know. A third question is, do you offer SSL pinning on iOS?
No, we do not offer SSL pinning on iOS. The reason for that is because Apple already provided that with their SDK.
Perfect. And it looks like we have one more question right now. And that question reads, do you offer optimization or shrinking on iOS applications?
No, that's also something we didn't have to do on iOS because the Clang compiler is already very efficient. So there is not a lot to shrink or optimize left for us.
Perfect. And if there are no other questions, I would like to thank Jonas for a phenomenal presentation. Secondly, I would also like to thank Guardsquare for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career.
Thank you. Have a nice day.